an electric field due to a charge ring. So I told you I would make a Python program calculating the electric field due to a charge ring, which I did in the previous video. Play this down below. So let's just go ahead and jump into it. Let's do a numerical model for the electric field due to a charge ring. Now, a couple things. Number one, it's a numerical value, so we need numbers. So let's just go ahead and pick some numbers for our values. And in particular, I need to say lambda, I'm going to use 9 times 10 to the negative ninth coulombs per meter. I'm just picking that. R, I'm thinking like a ring is like, it's like that big. So R is 2 centimeters, 0.02. I just picked something. And then let's say Z is 0.02 meters also. I think that's the only thing that we need to find the electric field at that location. So what are we going to do? So remember that the electric field due to a tiny point charge is this. This is the electric field due to a point charge, where R is the vector from RQ, the location of the charge, to the observation location, which we found before, right? We wrote this in partial spherical coordinates, partial Cartesian coordinates, and so that's my R vector for the charge. As phi changes, it changes, and that's my Z value as it changes. Oh, we did say this, dq was lambda r sine theta, which theta was pi over 2, times d phi. Yeah, that's important too, because that's that way I can do it in terms of lambda. So what we're going to do is to just, instead of integrating to find this, we are going to find a whole bunch of points in this ring and then just find the electric field due to a whole bunch of points. That's it. Okay. So let's just do it. And I'm going to make last time I didn't make it visual. I'm going to make it visual this time because I think that really helps to make sure you're on the right track. I'm using WebVPython. If you're not familiar with this, this has visual elements built into it so that we can make cool 3D stuff. But let's just start off with our constants, and then we can get going. So I'm going to say K is my 1 over 4 pi epsilon naught. That's 9 times 10 to the ninth. Let me take my glasses off. What did we say? R is 0.02, Z is 0.02, and then lambda, I can't use the whole word because it's a reserved word, is 9 times 10 to the negative ninth newtons per coulomb. And you can put your units in there and everything, but I'm not going to do that. Okay, so the first thing that we need to do is to make all of our charges. So how do we do that? Well, I'm going to do this in a couple different ways. I need d phi. But in order to do d phi, I'm actually going to say whatever n is. I'm going to pick how many charges I need. So n, let's say, is, I'm going to start off with something easy, 10. We have 10. So in that case, d phi is going to be equal to r. No, wait. Yeah, d phi is going to be, 2 times pi divided by n. That's my step size, right? And so then I'm going to use the equation for RQ. I have R, I have cosine phi, I have sine phi, and it's going to change phi. So let's do that. So what I'm going to do is to say phi is equal to 0. And then while phi is less than 2 times pi, make a sphere. Sphere. Position, let's just call this RQ. Let's put that right here, it'll be fun. RQ is the vector, just like we did before, of R times cosine phi, I almost did theta, R times sine of phi, 0. Just like before. That's just like before. Now I'm going to put a sphere there. I'm not going to give it a name. I'm just going to say sphere, and it'll put a sphere there. The position is equal to RQ. The radius is going to be equal to, let's say, put it as R over 100, and let's use color as color.yellow. That's what I did before. Okay. And now this loop will go on forever unless I say phi equals phi plus d phi. See? Let's run it. Do you think it's going to work? Sometimes I question myself. I don't know for myself that's actually going to work. It worked. Look at that. You can count them if you want. It is possible that you could like go over one step and have one too many point charges, but if I change this to n equals 100, no one cares. So now it's a nice ring. So let's leave it at 100. We can change it later. And I feel like this might be a little bit too small. Let's make this 70. You want it to look good, right? You want it to look good. Okay, next thing I'm going to do is to make RO, and that's going to be the vector 0, 0, z, which I have z. And I'm going to put a point there just so we can look at it. OBS, it's a sphere. Its position is equal to R. Position is RO. Its radius is, let's also put this as R over 70. And obviously this is the normal default color. So there it is right there. And that's in the z direction. If I rotate it, you can see there it is. Nice. Okay. Well, we're pretty much done, to be honest. Okay, so what I'm going to do is I know RO, I know RQ as it moves around the thing. I can just use my normal method to find the electric field due to each point charge and add it to the total. So the best way to do that is to set the total equal to the vector 0, 0, 0. Now when I calculate DE, I can add it to that value. So let's go down here. It doesn't really matter which part we do it in. I'm going to calculate DE. DE is going to be K. Oh, did I get DQ? I didn't get DQ. So DQ is equal to lambda times R times d phi. So I have DQ. Okay. So it's K times DQ. Didn't change, right? So I don't have to worry about that. Times R hat, which is going to be norm R. Oh, I didn't calculate R. Let's calculate R. It's going to be RO minus RQ. I have to do that in the loop. Right? Because every time I move to a different point, my R value is different. So I have to do that. Okay. And now I'm going to go over here and divide by the magnitude of R squared. I got my electric field. Now I'm going to add it to my total. E equals E plus DE. And then I'm done. And let's print that. Print E equals comma E newtons per coulomb. Let's see if it works. Well, it calculated something. Is it right? Okay, let's go back and calculate this again. ETZ. We did this before. I have right here my expression for the electric field. You can't see it quite, but I did write it down. Okay, electric field due to the point charge we derived. So I'm going to write this as K times 2 pi times R times lambda. I'm looking at the board. Times Z. Yeah, I thought there was Z. Divided by R squared plus Z squared to the 3/2. And let's print that too. Print ETZ, so ET is the theoretical Z component, ETZ. ETZ, newtons per coulomb. And we're not done after this, don't worry, don't leave just yet. The bell doesn't dismiss you, I dismiss you. So here's my Z component, 9,866, and so it's close. It's pretty close, right? And these are not 0, but they're pretty close compared to this. 89 is very large if you're just looking at it as a number, but it's very small compared to this. And we can fix this. If we can do 100, we can do 1,000, right? So I can do 1,000 points. So all I have to do is add a 0 right here and run it again. And look at that. Now it's a lot better. Not perfect, but better. Why are these two not the same? Why are the X and Y values not the same? Because it depends on where those charges are, right? In the X direction, if they're completely opposite of each other, they may, or in the Y direction, they may cancel better than in the X direction. So, okay. Let's leave it at 1,000. I'm going to add an electric field. Oh, wait, let me run that one more time. So we're here at 9,000. Okay, so we did this before. Now I want to draw the electric field as a vector. To do that, the electric field is 9,000, but the arrow is in meters. So I don't want a 9,000 meter long arrow because it's too big. I won't be able to see anything else. So I need to scale it down. So I'm going to make a variable called e scale, and let's make that 1 times 10 to the -5. Let's see if that works. If we need to make it smaller, we make it smaller. So down here, I'm just going to add an arrow. Arrow position is at the observation location, RO. And then the axis is going to be equal to E scale times E. And let's make it color dot cyan, just like we did before. And there's my giant arrow. It's too big. Let's make it 10 to the negative 6. Let's try that. That might be too small. That looks good. Look at that. In the z direction. Now, notice that we didn't force it to be in the z direction. We calculated it. And just like before, the nice thing about this method is it doesn't matter where our observation location is. We can put it wherever we want. We can put it right. Let's just change it. Let's change the observation location to z, 0, z. So it's in the x-axis. Yeah, whatever. And there it is. You can't really see it right there. Let's zoom out. Zoom in. So it's not in the z direction anymore, right? So it has some component. Okay, do you want to do something fun? Let's do something fun. Okay, so what if I want to do a whole bunch of electric field arrows? Let's do that. Let's just move at that same z value and move in the x direction and plot some things. So I'm going to have to do some tricks here. The first trick I'm going to do is to make this electric field calculation a function. So I'm not going to do this the best way. I'm just going to do it the way that makes sense, the easiest way. So I'm going to cut this and put this right here. And then I'm going to say, oh, let's call this ET, temporary electric field. And then I'm going to call this ET. And then I'm going to call, I'm not going to print, I'm not going to do this, I'm not going to do this, I'm not going to do this, I'm not going to do that. Okay. So now what I want to do is to put all this in a function. I'm going to say def E, and I'm going to give it an RO. But I already have an RO. So let's call that RTO for temporary. So I want to pass it a vector, and it's going to return an electric field. So I'm going to use the charge distribution that I have. Now there's a couple ways you could do this. You know, you could store all your charges in a list and go through that list every time. I'm just going to remake the charges every time because I don't really care. Okay, I'm just trying to make it simple. So I'm going to put all this stuff in my function, and then what, oops, I do this every time. I don't know why it does this. It makes me a little frustrated. Where did my cursor go? Okay, and then I'm going to return, once I'm done with this, I'm going to return, oh, up here, you know what? I have phi is 0. I'm going to cut that and put it down here, right? Because that way, I'll always start with phi equals 0. I'm not using the best rules for functions here, okay? So I'm sloppy. But it's okay to be sloppy. If, you know, the most important thing is to get it done. So I'm going to return ET. Oh, and I missed this too. This should be ET. Okay. So let's just test it out. Let's just print E at RO. And I need to change R. I passed RTO, so this has to be RTO right there. Let's see if it works. We're just testing our function if it gives us a vector. Yeah, it did, and it looks like the same value, so it looks good. Okay, so now what we're going to do is to move our RO around, and then we're going to make an arrow at every place. So let's say dx is going to be 0.01. I don't know. And so RO is going to be, I'm going to start it at negative R 0 Z. That's where I'm going to start it. I'm going to move it in the x direction until I get to R. Right? So I'm going to move across the disk. So I'm going to do 1.5 times R just for fun. So while RO dot x is less than 1.5 times, oops, not there, 1.5 times R. So I'm going to move it. So the first thing I'm going to do is I'm going to do this in one fell swoop. I'm going to draw an arrow there. So I'm not going to name it. Arrow position is equal to RO. Axis is equal to E scale times, here we go, watch this, E, the function of RO. So I can pass it to that in the function. It's kind of cool. And I'm going to give it a color equals color dot cyan. And then I'm going to move my RO. So RO equals RO plus vector dx0, 0. So it should hopefully get there. Okay. So we should get a bunch of arrows across that ring. Let's just see if it does. And I didn't even save this. Let's see. Let's save it. E field ring. I'm going to give you the code. Don't worry about that. Let's run it. Check that out. Zoom out. And it didn't go quite as far. Why didn't it go right over here? Maybe because my dx is too small. Let's just go down here. Why didn't I want to go a little bit further? Let's just do 1.6 r. Let's see if that works. I guess it just didn't get to that last element because of my step size. There we go. Now it looks better. What do you think about that? You like that? Okay. So if you want to, as a homework, you could take this. You could move in the x direction and the y direction, get a 2D map of electric fields. That'd be pretty cool. But once you see the idea of how to do that, it's not that big of a deal. So there you go. Electric field due to a ring, numerical calculation, VPython code down below, playlist down below, and I'll talk to you later.